Today is lecture number 12, analog circuit design. However, this particular lecture is not on analog, but it's some revising your fundamentals on frequency response, or you can say that the body plot. There are many other ways to find out the stability of the system. However, this is one of the technique through which you can find out whether your system is stable or unstable. And I believe that you have studied this thing in your previous course called control theory, or maybe other places like signal system, and depending on your course curriculum you must have seen it somewhere else. However, I'm going to touch this with a little bit different way, and I'm going to give you the key points how to make the frequency response using body plot. So there is no calculation, there is directly the trick to draw that. That's it. So I should not say that even it's a trick, but whatever you have studied, that is what going to be refreshed over here without any physical calculations. So Bode plot is the one which is going to draw the frequency response. Now the plot is composed of two things. You are going to make the magnitude as well as the phase plot. So combining these two are known as the Bode plot. X-axis is the one which is in radian per second, sometimes in also in hertz, depending on how you are plotting the plot. So x-axis is generally we are keeping it log scale. The reason is we want to go from 0 hertz or very low frequency to very high frequency scale. So if it is on log scale, you can move from very low to very high frequency very easily. However, if it is on linear scale, it's very difficult. That's why its log scale is very important. Similar, the case of magnitude response is measured in terms of decibel. Decibel is already known to us. It's 20 log 10 base and some ratio. That is going to give you the decibel, and the phase response uh, is in angle, or it's in a degree. So in general, we want to use it for the for to determine the stability of circuit, or maybe this is applicable to any system. It's not only circuit, but we are calling circuit because we are studying analog circuit designing. So now there are some of the measuring factors used for stability. So one of them is small signal gain near DC. Some people call it low frequency gain also. This is AC gain. Sometimes it's also differential gain also. If your circuit is differential, we are going to study this maybe after the frequency response, but differential one is deciding the differential gain. Moreover, sometimes it's very useful to see that how much gain you are achieving at at the bandwidth, where it might be 3 dB. Sometimes you are also interested in unity gain bandwidth. This is very important term. We'll understand it in later stage, where we want to find out the gain margin and phase margin. These all these things are already defined and already known to you, but I am redefining with some new names, like our analog circuit designers are going to call it GBW or the UGBW, which is very important. You must have studied in your control course, where it's known as gain crossover frequency. And after drawing this magnitude and phase plot, you are going to derive phase margin and gain margin, and through that you can find out whether your system is stable or unstable. Now looking at this is very easy. Just you need to find out the poles and zeros and the order of the system. So here you can see that the order of the system is actually 4, because there are highest degree of numerator is 4. The poles are available at like 0 0, -1 and -3, and zeros are available at -0.5 and -1.5. However, if you want to find out the type of the system depending on how many number of integrators are there in your system, or you can say that the number of poles available at the origin is going to decide the type of the system. So this as the type of the system is 2. And if you are interested in small signal AC gain, or some people call it low frequency gain, or you can also call it DC gain. So any one of them is actually depending on how much you can take. If you are going to write it in the form of tau s plus 1, what are you going to see? So that is 0.5 1.5 divided by 1 multiplied by 3, that is going to give you the whole transfer function in tau s plus 1, where it's written by s by 0.5 plus 1 times s by 1.5 plus 1 and divided by s square, s by 1 plus 1 and s by 3 plus 1. This quantity is going to be known as the small signal AC gain, or the low frequency gain, or sometimes DC gain. DC, but it's not DC, it's very low near DC, so that's why it's also known as DC. However, so this is going to decide what is the small signal gain, or this is same as what we were talking about the first term. Now let's revisit what you studied maybe in your uh, like previous course. So this is the conclusion or the summary of what you studied. And like, I'm not going to go through the derivation of these things. For derivation you can separately go through some control course. But single pole frequency is going to contribute minus 20 dB per decade, and single zero frequency contributes plus 20 dB per decade. So if there are multiple zeros or poles, accordingly you have to change the slope of the system, right? Or the slope of the system contribution. And the slope of the particular frequency is calculated with respect to previous accumulated frequencies also. So then you can have such kind of things. So let's learn how to make the magnitude plot. Magnitude plot has x-axis is in frequency, y-axis is in decibel, and yeah, each of them are like x-axis has uh, 1 decade. Is you can see like such kind of things you are going to see in your semi-log paper. So each one of them is actually indicating one number, but from going from one to another block of the frequency, it's 1 decade. So if it is zero point 0.1, this goes 1, this goes 10, and the next one might be 100, and so on. So you can have the value as big as you want, and accordingly you have to start from the minimum number. Note that on x-axis you are not going to have 0 hertz ever, because it's in log scale. In log scale 0 is not at all possible, right? However, if you're looking at the y-axis where you are seeing the 0 dB line, let's write it down in red color. 0 dB is not 0, but it's actually 1 volt per volt, because 20 log 1 with 10 base is going to give you 0 dB. So 0 dB is the one where your gain is 1 volt per volt, or you can say that there is no gain. It's exactly transferring your V in and V out are exactly same, and that is the point. We are going to call it the 0 dB line, or you can call it unity gain line, where there is no gain but it's unity gain, right? So this is already known to us. Now let's go ahead. You might have three different possibilities of the transfer function. When you are starting, you have to have either like three possibilities are there. When you are going to start, you might not have, like, there is only DC gain available. There are three possibility when there is only DC gain or the small signal AC gain, right? Or let's call it low frequency gain, just to avoid. Here you have pole at origin, and here you can have 0 at origin. So in that case, you may have to start with a different start of the magnitude plot. In the first case, you are going to start with 20 log k. That's the contribution by k. We are not considering right now s plus a. We are going to talk about this maybe later stage or on the next slide. So with respect to any frequency, the contribution of this one is 20 log k in decibel, and with respect to frequency. Whereas in the case of pole, you should know that on x-axis you should go to the point called k, and as there is one pole is going to give you minus 20 dB per decade. So you have to go back by 1 decade and go up by 20. right? So this is 20 and you have to connect all these points. So this is going to make minus 20 dB per decade with K by S. This is happening because of the fact that the magnitude of this one is 20 log K minus 20 log of omega. So at the frequency of K, sorry, at the frequency of K, this becomes 0 dB. That is what I drew over here. And similarly, for this case, at 1 by K, you need to go and you need to draw plus 10, 20 dB per decade. For that, you can go to 1 by K times 10 and you have to go up by 20 dB. So this is going to give you plus 20 dB per decade for the case of K by S, right? So this was the brushing up all your fundamental. Those things can be seen over here. So K by S is going to give you this kind of things. If it is K times S, it's going to give you such kind of plot. You need to see that it has to pass through 1 by K. But 0 dB is line is there. So now there might be the case that it's not at origin, but there is a transfer function which is at K times S plus X, where K is small signal or small signal low frequency gain, and S plus X is the one which is going to tell you the the zero location. So here small signal gain is K by X times S by X plus 1. This is very important to do that, because just to find out what is required. So for assumed K, you can have, you need to find out 20 log K by X over here, and it's a constant line. When you are going to have the frequency of X, thereafter you have to draw plus 20 dB per decade. So you can have such kind of plot. But if you have to draw such kind of things, you can start with, first of all, you have the small signal gain, or K value is like this. So it's 0.25. So K is 0.25 over here, and 20 log K is needs to find out by 0.25 in decibel with, and there are various poles and zeros. There are poles available at 2 poles available at origin, and thereafter minus 0.5 at 0 and minus 1 pole, and minus, sorry, yeah, and then minus 1.50 and this minus 3 as. So this is, all these are poles and all these are zeros. So you need to just draw that with different location of the frequency. So you can draw that, but you have to start with the K by S square. So at the origin there is minus 40 dB per decade uh, of the minus 20 dB minus 40 dB per decade of the slope. So you have to go to the frequency called 0.25. At 0.25 this is going to be equal to 0, and you have to draw the slope of minus 40 dB per decade. This is going to give you the frequency response as you want. But after this, this is for 2 poles at origin. For the case of next frequency, which is 0 minus 0.5, so 0.5 is going to give you next slope, which is, it's going to add plus 20 dB per decade, and effectively it's minus 20 dB per decade contribution. Then you have to go to 1, where again it's going to give you minus 40 dB per decade, and after 1 you have to go to 1.5. Let's say this is 3, minus 20 and plus 40 dB per decade. So effectively you are going to see the darker line only as frequency response. So this is what you have studied, and this was just revision. So that's why I'm going very fast on this. So for different frequency response, you can practice and you can find out the plot. But here most of the important part which is playing the role in terms of finding out the stability is its phase margin. So how much phase margin is contributed by your frequency response. So there are designing key points are there, that your phase margin should be more than 45 degree. This is with the reason that when you are going to keep your system in feedback, and if your input is some step response, this is with voltage with respect to time, and output may have some rings. So this is all depending on how much ringing you are seeing, that will be acting as phase margin, by the way. Notably, when it's 60 degree phase margin, it's it's a system where there is no ring. For phase margin of 60 degree or greater than 60 degree, there is no ring. Just remember this. This you can see from the simulation, and this is from practice, you can see that. So so there is no ringing, and this response becomes sluggish also. And with 45 degree you will see some of the ringing. So the system is stable if your phase margin is greater than 45 degree, and you know that if you are greater than 60 degree, there is no ringing at all. So understand this. And this is by some practice. You have to do the simulation and you will realize that this is going to happen. There is no uh, like these numbers are coming from there only, or you can derive it also, but most of the time these things works. And these things are depending on the fact that your time constant is that much enough that it's get settled before the next cycle of clock is happening. So if your system requirement is much faster than this, then you have to make sure that your system gets settled much before that. Otherwise this won't work. We will understand this maybe during the time of designing some system like differential amplifier or maybe operational amplifier and so on. But for this fact, we can see that you have to just remember that your system, to become stable, it has to be more than 45 degree. In 45 degree also it's going to be oscillating one, or you can see the ringing. If you don't want to see ringing, make sure that you are achieving 60 degree phase margin at least, or if it is more than that, it's very nice. But this is happening at the cost of the slow down system, or the system becomes sluggish. So that's the characteristic generally. So let's see what is happening in that case. Let's look at the system where there is a single pole system. There is only and only one single pole system, and it whose transfer function is like this. Let's And so there is one frequency. Okay, here it's P1 is written, so let's write down P1, right? So here you can see that K is here. So that is a you have to apply the Bode plot where you will start with 20 log K. You'll draw the the constant line, and at P1 you are going to observe minus 20 dB per decade, right? And it will be for like infinite frequency, it will follow the same thing, and it's going to touch at the frequency which is known as UGBW, or unity gain bandwidth. This is very important to finding out phase margin, because phase margin is measured at UGBW. For that you need to see what is happening in terms of phase. So according to the theory of phase, you can say that if there is a pole in a system which looks like this one, so you can see here at omega much lower than p1, then the phase is actually 0 degree, right? Because this is becoming 0, so it's 0 degree, or at omega equal to 0 degree, the phase is 0, and when it's much lower than p1. Now let's look at the next level of when your omega is much higher than p1, which we can call it infinity. The phase is equal to minus 90 degree. Very nice. But what if omega is exactly equal to p1? Then the phase equal to minus 45 degree. So this is for single pole. But if there are two poles, the whole theory becomes different, and omega equal to 0, it's 0 degree, and at omega equal to p1, omega equal to infinity, this phase becomes minus 180 degree, and at exactly at p1, this is going to be 90 degree. 135 degree. So you have to take that accordingly, right? So 90 degree will be added. That is the main thing happening here. So now let's use that one on top of another thing. If there is a 0 in a system which looks like this, using same theory, you know that phase equal to plus tan inverse omega by z1, and phase contribution is at omega equal to 0, it's 0 degree, omega equal to plus 90 degree at omega equal to infinity, and omega equal to plus 45 degree at omega equal to z1. So these are the already known facts which we have kept it here in the case of phase. So here you can see that we have only one frequency. So phase wise, at low frequency you are going to have 0 degree phase, and at infinity you are going to have minus 90 degree of phase. However, in between, when we are connecting the line, you can see that at frequency of p1, the phase contribution is minus 45 degree, and accordingly you can have this slope, because it's not going to happen instantaneously. Around p1 you can have this 0 to minus 90 degree. It's depending on the dynamics of the overall system. It depends on k and other things. So in this case 0 to 90 degree, and it's minus 45 degree, you can see that at UGBW the phase margin is measured using 180 plus contribution of phase. So you have to see what is happening at UGW, and you have to find out the phase. So here I can see that the phase margin or available phase is minus 90 degree. So phase margin becomes plus 90 degree. So note that what we have studied and what we have agreed on is your phase margin has to be more than 45 degree plus 45 degree to be in stable system or the stable mode of operation. So we know that if you have the single pole, your system is always stable. It's very nice, no problem. But what if there are two poles? One more pole is inside this one. So at pole P1, you can see that you are going to have minus 45 degree of contribution of phase, and at exactly at P2 there is minus 135 degree of contribution, because for pole P1 at omega equal to 0, the contribution is this one is 0 degree. At omega equal to infinity, the pole contribution is minus 90 degree, and omega equal to P1, the pole will have phase contribution of minus 45 degree. So you can draw that, right? So 0 degree, and exactly at this one it's minus 45 degree. But when we have the pole number 2, which is again having identical characteristic of pole P1, but it's going to be added on top of the previous contribution. So at low frequency, or you can say that if omega is more than P1, but much lower than P2, then the contribution of phase is going to be equal to minus 90 degree, which is coming from here. Similarly, omega is much higher than P2, or at infinity, the phase contribution is minus 180 degree, taking into account minus 90 degree also. And at exactly equal to P2, the phase contribution is minus 45, plus it has to taken into account the previous minus 90 degree coming from the omega equal to infinity, so it's going to be equal to minus 135 degree. So adding all these, you can see that at pole P1 the contribution is minus 45 degree, at pole P2 the contribution is minus 135 degree. So right now let's assume that the plot looks like this one as I have drawn, and I'm interested in finding out the phase margin. So for that I need to find out what is the phase available at UGBW. So you can see at UGBW the phase availability is minus 180 degree. So phase at UGBW phase at UGBW is equal to minus 180 degree, and if I want to find out the phase margin, then I have to just add same thing with 180 degree. So I'm going to have phase margin of 0 degree. So 0 degree is not good, because we agree that phase margin has to be more than 45 degree just to have the stable system. So this system is unstable, right? Because this is happening. But now main thing happens if you are able to move P2 somewhere here, that's near to UGBW. Then as you are increasing this, your phase margin is going into positive side. So earlier when the phase contribution was minus 180 degree, now the phase margin contribution is not minus 180 degree but little bit higher than that. Then your phase margin is becoming positive, right? But still it's not 45 degree. So to achieve 45 degree, what I'm saying or what I'm proposing, let's keep this pole exactly on top of UGBW. Then what is going to happen? If you do so, so pole number 1 and pole number 2. Pole number 2 is exactly on UGBW. Pole number 1 is here where it was. This is 20 log K in decibel with respect to frequency. So this is going to give me minus 20 dB per decade, and this is going to give me minus 40 dB per decade. Now I'm interested in drawing the phase plot. So in phase, in degree with respect to same, okay, I made a mistake. Phase with respect to frequency, so phase in degree and this in frequency. And it's like common frequency axis over here. So at P1 we know that this is going to give me 0 to minus 90 degree of phase contribution, and at P1 the contribution is minus 45 degree. So here it's minus 45 degree and it start with something like this. So this is going to be minus 90 degree, this is 0 degree. By the way, notably this line is 180 degree. This is all because of the fact that we are drawing everything near the characteristic equation where 1 plus gh equal to 0. So mod gh is equal to minus 1, or you can say that the magnitude of this one, we are looking for 1 with 180 degree phase shift, right, from this equation. So that's how like this phase margin came into picture. So we know that pole 2 is also going to give you 0 to minus 90 degree, and at P2 it is minus 45 degree, but it has to add the last signal which is available at minus 90 degree. So all the things has to be added with minus 90 degree. So the contribution of pole 2 will be minus 90 to minus 180 degree, but at pole 2 it will be minus 135 degree. So exactly at pole 2 you are going to observe minus 135 degree, and thereafter it's 180 degree at infinity, right? So here you can measure the phase. So the phase becomes 180 minus 135, which, sorry, so with respect to 180 this phase is become something like 45 degree in minus sign. Yeah, so phase margin, if you look at this, okay, if you look at the phase margin, it becomes, okay, not this one, I made a mistake where I was, oh, I have not drawn that. So at this one it's minus 45 degree, so you have to add with 180, so you'll get what is actually required, right? So you can find out the phase margin. So at UGBW the phase margin is, okay, this is a mistake over here. So if you measure this, phase margin is equal to 45 degree because phase contribution is minus 135 degree. I need to contribute with respect to 180 degree, so this becomes 45. So this is a very useful observation. If you are going to keep pole 2 exactly on UGBW, the phase margin is 45 degree, or this is the point from which the system can become start calling itself as stable one. Now if you want better system than this one, what you can do, you can take this pole away from the UGBW. So if you go little bit higher than UGBW, you will have much better value. So much better value in terms of stability, because we agree that phase margin should be equal to or more than 45 degree. So here, as you are taking this P2 higher than UGBW, means your phase margin is improving or becoming greater than 45 degree. So if you want to have 60 degree, take it accordingly, little bit higher than what you required. So even if the system is two pole system, it's all about where you are placing your pole. So here you can see that the system is second order. However, pole 2 is outside UGBW, so that the system act as a first order system only before UGBW. Then this kind of system is called single pole dominant system. Because we know that if it is single pole system, always it's going to give you phase margin more than 90 degree. Right, 90 degree means there is no ringing, no fluctuations, no problem. So all single pole systems has more than has phase margin more than 90 degrees, so there is no problem. Whereas in the case of two pole system, if pole 2 is inside UGBW, it's going to give you ringing in terms of poor phase margin. If UGBW is much lower than pole P2, then you are going to have the phase margin of 0 degree. If UGBW is exactly equal to P2, your phase margin is 45 degree, and if it is more than UGBW, the second pole, then you are into the safe region where the system act as a single pole and the contribution of phase margin is 90 degree. So even if this is second order, you're going to keep the second pole much higher than UGBW. This is also the the trick to design a good system which is stable. And what we are talking, all these things, these are in open loop system. Note that this is not, still now we have not started the closed loop. So this is for where to keep the pole to. Similarly, now we can talk about some more things like three pole system. If you may have three poles, then system becomes worse. There are one, two, and three. Each one of them are going to contribute in phase minus 20 dB per decade, 40 and minus 60, and this is your UGBW. So you can calculate the phase. So phase at omega equal to P1, the phase is minus 45 degree. At omega equal to P2, phase is equal to minus 135 degree, and at omega equal to P3, 90 degree more, so it becomes 225 degree here, right? So after drawing this, you will understand that so this becomes minus 45 degree, this becomes minus 135 degree, and this becomes minus 225 degree. So your phase at UGBW might be minus 270 degree. If pole 3 is much lower than UGBW, then your phase margin is actually becoming minus 90 degree. So this is the phase margin you are achieving if there are three pole system. So what is the key to make it positive? Or if you keep P3 outside UGBW, means much higher than this one. If P3 is here, then you know that pole 1 and 2 are inside. So now the contribution by pole 2 is dominating over here, and here you can observe minus 180 degree, and at pole 3 you're going to observe minus 225 degree. But we don't care about this, we care about the UGBW. So right now phase margin is 0 degree because the phase contribution is minus 180 degree. So adding to 180 degree is going to give me 0 degree of phase margin. Now this is also not satisfactory. We need to make sure that the system is stable when the phase margin is greater than 45 degree. So this is only possible when we take this P2 also outside. If you take it outside, means if you're keeping exactly on UGBW, you are going to see the phase margin equal to 45 degree. If you achieve more than that, you are going to have phase margin more than 45 degree. And when it's much higher than UGBW, you are going to achieve the phase margin of 90 degree. But 90 degree is also not required. The requirement might be like greater than 45 degree or sometimes 60 degree. That's self sufficient to make the system in stable mode. However, sometimes it depends, because taking all these things outside in frequency domain is actually costing in terms of current. So we'll see this in later stages, that how to take these poles outside UGW, because it's costing the current or it's costing the area. So it's it's not a wise decision sometimes to take exactly pole to much higher than UGBW to achieve phase margin of 90 degree. If you are happy with 60 degree, that is also good enough, because that is going to reduce some power, right? So this is very important thing, and we'll study this in the next phase of learning, which is called frequency response. And we'll come back to again the MOSFET amplifiers, single stage amplifier and differential amplifier, and later on we'll go to the operational amplifier to understand that how these poles and zeros are actually moving and how to control them. So there are lots of techniques like pole splitting, Miller compensation. All these things will be studied over here. Okay, so thank you for today.